This is Common Core State Standard Support Video in Mathematics. The standard is 8.G.A.3. This standard reads, describe the effect of dilations, translations, rotations, and reflections on two-dimensional figures using coordinates. First, let's look at how this standard relates or connects to other standards that deal with this area of translations, rotations, and so forth. In the same grade level, a precursor to this one is standard 8.G.A.1, and it basically talks about the properties of these different transformations. For example, part A, they're talking about lines being taken to lines and segments being taken to segments of the same length, angles being taken to angles of the same measure, and parallel lines being taken also to parallel lines. This 8th grade standard sets the foundation for something a little bit more complex at the high school level. Standard HSGCOA4 is about developing definitions of rotations and reflections and translations in terms of angles, circles, perpendicular lines, parallel lines, and line segments. In the same grade level, we have standard 8.G.A.2, which is just prior to the one that we're addressing, and it deals with congruency, but it connects it to the idea of rotations and reflections and translations. Following 8.G.A.3 is standard 8.G.A.4, which again is very similar, except this one deals with similarity, and it ties that idea to these different transformations. Notice though that 8.G.A.3 involves dilations, which is of course a little bit different than congruency because of the idea of a scale factor. So let's look at dilations. What else in the standards is connected to this idea? Well, back in 5th grade, we had standard 5NF-B5, and it talked about interpreting multiplication as scaling. Now, the important pieces here are this idea about multiplying a given number by a fraction greater than 1 results in a product greater than the given number. And also, if you multiply a given number by a fraction less than 1, that results in a product smaller than the given number. So that kind of parallels what happens with dilations. With respect to dilations, this standard 8.G.A.3 sets the foundation for something more complicated in high school. This is addressed in standard HSG.S.R.T.A.1 that talks about verifying experimentally the properties of dilations given by a center and a scale factor. One of the things that is addressed at the high school level is this idea of the center of the dilation, as opposed to no mention of that in 8th grade. However, you do have this idea of a scale factor, and that's really important. That idea of a scale factor connects to a ratio. So back in 6th grade, we have standard 6RP that talks about understanding ratio concepts and using ratio reasoning. Then we have a 7th grade standard, 7RP, that deals with analyzing proportional relationships and using them to solve real-world problems. Although the exact phrase scale factor is not used specifically, teachers need to connect dilations to these clusters of standards that focus on proportional reasoning, because that is what happens with dilations. You do have a scale factor that has a huge impact on how large or small the dilation will be in comparison to the original figure. Let's see what other standards are connected to the idea of reflections. Back in 4th grade, we had standard 4.G.A.3 that talked about a line of symmetry, which is an integral part of the idea of a reflection. Now, this 8th grade standard talks about these different transformations, but with respect to coordinates. So connected to that idea is standard 6NSC6B that talks about understanding the signs of numbers in ordered pairs. But what's especially important is the latter part of this standard that talks about recognizing that when two ordered pairs differ only by their signs, the locations of the points are related by reflections across either one or both axes. So let's start off with translations and see how two-dimensional figures are impacted when it comes to the coordinate plane. Let's start off with a basic triangle, and there's our coordinates. And let's say we're going to shift it to the right and up. So let's shift it, and this is where our new location is. Here's our new coordinates for each of the three vertices. Well, let's see what happens. If we look at all of the x coordinates, if we pair them up, we have 3 compared to 10, 6 compared to 13, and 3 compared to 10. Let's see, it looks like there's a difference of 7. So for all of the x coordinates, the matching pairs, the difference is 7 in the positive direction. If we look at the y coordinates, let's see, 8 compared to 12, 8 compared to 12, and 13 compared to 17. That's a difference of 4. And that reflects the idea that we shifted upwards by 4. Let's look at another translation. We start off with the same original, but this time let's shift to the left and down. Here is the new triangle in its new location with the new coordinates. If we investigate the x coordinates, 3 compared to -5, 3 and -5, and 6 and -2. That looks like a difference of 8, and they're 8 smaller, which reflects a shift of 8 to the left. If we examine the y coordinates, 13 compared to 10, 8 compared with 5, that looks like it's a difference of 3, and it's 3 less, and that reflects our shift of 3 down. So the translation here involved a shift of 8 to the left and 3 downward. Each of the corresponding pairs of x and y coordinates reflected those. If we generalize this, if we start off with our original coordinates, we'll call them x and y. Our new coordinates would be, well, let's see, if we let h be the horizontal shift, then the new coordinates would be, for the x, you simply add whatever the horizontal shift was, and by add we mean you could be adding a positive or a negative number depending on the direction of the shift. If we let v be the vertical shift, then for the y coordinate it's the same deal. You're going to add the vertical shift to the y coordinate, and of course by add we mean adding a positive number if it's an upward shift and adding a negative value if it's a downward shift. We need to lay the foundation as to how some of these figures are labeled. If we start off with our original figure being triangle ABC, and there's our coordinates for this particular example. Then we did a translation where we, in this case, shifted to the right and up. Notice that in order to better try to match up each of the vertices, we're labeling them using the same letters, but to distinguish one from the other, for the new position, A would be A prime, B would be B prime, and C would be C prime. So our new triangle, after being shifted, is triangle A prime, B prime, C prime. And there's our new coordinates. Again, in the future, this is what students can expect as far as how vertices are labeled after some type of translation. Now let us look at reflections. Let's start off with a triangle, and we're going to reflect it across the x-axis. Here's our coordinates. And let's color code the legs of the sides so that we can identify each one pretty quickly. If we start off with a 0.53, if we reflect it across the x-axis, there's our new location. If we reflect the 0.83, there's its new location. And then we reflect the 0.29. Here's our new coordinates. Now we connect all the vertices and color code them to make sure that we can again distinguish which side is which. If we examine what happens with the x coordinates, well, let's see, both of these x coordinates are still 2. Both of these are still 5. And the new x coordinate here is still an 8, like the original. So if we let x and y be the original coordinates, so far the x coordinate stayed the same. And now we examine the y coordinates. Let's see, it was 9, but now it's negative 9. 3 versus negative 3. And another 3 versus a negative 3. So it looks like our y coordinates, when we reflect across the x-axis, will be the opposite value. Now, notice that this should be described as the opposite of y, not negative y, because that can be very confusing. So it's very important here that we not confuse things by saying negative, because it may not in fact be a negative number. We're just talking about the opposite number, the inverse of it, the additive inverse, to be more exact. What about reflections across the y-axis? Let's reflect this point across the y-axis, then this vertex, and the third vertex. Let's figure out our new coordinates. Let's connect the vertices and color code the segments accordingly. Let's examine what happens with the coordinates. Well, let's see here, we started off with a coordinate of 2 for the x, and now it's a negative 2. For this point, originally we had a positive 5 for the x coordinate, now we have a negative 5. And then here we started off at 8, and now it's negative 8. To generalize, if the original coordinates here reflecting across the y-axis were x, y, well, let's see, it looked like on the x coordinates, the values for x are now the opposite. They're the opposite sign. Again, we need to describe this as the opposite of x, not negative x. For the y coordinates, let's see, still both 9s. The 3 remained a 3, and that 3 remained a 3. So here's our generalization. If we start off with original coordinates x and y, if we reflect across the y-axis, the x coordinate will be the opposite sign, and the y coordinate will stay exactly the same. What if we take a figure and reflect it across both the x and the y-axis? If we reflected the original triangle across the x-axis and the y-axis, these would be the results. And now, regardless if you take the triangle that was reflected across the x-axis or the y-axis, when we take this vertex and reflect it, here's where we are. If we take that vertex and reflect it, there's our new location. And then we reflect this point. Let's connect those points, color code our segments, and let's figure out what our new coordinates are. Now let's compare to see what happened with the x coordinates and the y coordinates. Well, it looks like, let's see, if our original coordinates are x, y, our new coordinates, well, on the x's, all of the values are the opposite signs. So whatever the original x coordinate is, the new coordinate for the x, when we reflect it across both axes, will be the opposite of x. And when we look at the y coordinates, same thing. All of the values for the new coordinates on the y's are the opposite sign. So it looks like if our original coordinate vertically is y, then the new coordinate will be the opposite of y. Let's try another example just to be on the safe side. Let's say we start off over here in the second quadrant. And we reflect across both axes. So here's our new triangle, our new location. Let's see what happened. Here's our original coordinates. Here's our new coordinates, and we're labeling these like we mentioned a while ago. Triangle ABC becomes triangle A prime, B prime, C prime. Now let's compare the coordinates. If we look at the x's, yes, they're all the opposite signs. And when we look at the y's, the same thing. All of our y coordinates are the opposite sign of what they started out to be. Again, note that our negative sign, subtraction sign, whatever you want to call it, is being interpreted as the opposite of, not negative. Now, here's something interesting. This is what can lead to confusion if we're not careful. Okay, notice here the way that the original coordinates are labeled and the way the new coordinates are labeled. Notice here that the sign is being interpreted as negative rather than the opposite of. So in other words, the way that it's labeled here, being that it's in the second quadrant, this is saying that our x coordinate will be negative and our y coordinate is positive, as opposed to being in the fourth quadrant, we would have positive x coordinates and negative y coordinates. But again, it's not a good idea to do this with variables because the meaning of that sign can really confuse students. So labeling it like this is not a good idea. You should always start off labeling your original coordinates as just x, y, and then worry about if it's a positive or negative number once you figure out what the coordinates are. So far we've talked about reflections across the x or the y axis, but what about other lines of reflection? It really doesn't specify in the standard whether or not this should be included, but just to be on the safe side, well, let's see what happens when we reflect across a vertical or horizontal line, something other than the x or the y axis. So let's say we have a line of reflection that's a vertical line with the equation x equals to 9. Let's start off with this triangle with these coordinates, and let's see what happens when we reflect it across this line. Here's our new coordinates. So let's see what happened. Let's see, on the left we have 6 and 6, we have 6 and 6, and we have 12 and 12. It looks like our y coordinates are still the same value, which makes sense because there was actually horizontal shifts that happened here. Nothing happened vertically. So if we generalize this, if we have original coordinates of y, our new coordinates will also be y's. The same thing, no change. Now let's see what happens with the x coordinates. Now this is a little bit different because we're not at an axis. Now notice that the x coordinates for those top two vertices, one shifted 2 to the right and the other shifted 2 to the left. So we have a 7 versus an 11. Then for these two vertices, we shifted 5 to the right on one, and we have a shift of 5 to the left on the other, comparatively speaking, with respect to this new line of reflection. And then for the outermost vertices here, let's see, we went 8. We're 8 away from the line of reflection on one in the positive direction, and we're 8 away in the opposite direction for the other one. So this is what we have. X is the x value for our line of reflection. In this case, it was 9. When we generalize the little subscript r, that's what that indicates, that it's the x coordinate for our line of reflection. So for the original triangle, I was a certain horizontal distance from the line of reflection, and that's reflected with the variable h. So for the original, I was so much of a distance to the right of the line of reflection. And then notice that once the reflection happened, I was the same distance from my line of reflection, but in the opposite direction. And that's how come you have the opposite of h as far as the distance. So in one case you're going to reflect to the right, and in the other case you're going to reflect to the left. Let's try a horizontal line of reflection. Let's say y is equal to 5. And let's start off with this triangle. And let's reflect it across the line y is equal to 5. Here's our new coordinates, and we color code our segments. What happened with the x coordinates? No change. 2 and 2, 5 and 5, 8 and 8. And again, that makes sense because there was no shift to the left or to the right. All the shifting took place vertically. So if our original coordinates are x, then the new coordinates for the x value will stay the same. Nothing changes there. So now let's look at the y coordinates. We have our line of reflection being y is equal to 5. Let's see, for that one pair of coordinates, one is 9 away in one direction, one is 9 away in the other direction. Let's see, we're 3 away on this set, and we're 3 away from the line of reflection in that set, just in opposite directions. So here's how we state that algebraically. If this y subscript r is our y coordinate for the line of reflection, then in this case the original y coordinates were a certain vertical distance away, and it was above it, so that's how come we have the plus. And then when we reflect across that horizontal line, then the new coordinates would be whatever the y coordinate is for the line of reflection, and we would subtract the vertical distance from the line of reflection. One of the things that we have to be careful about here is that students can see the numbers and everything, but when we generalize and we use variables, it's very, very important that students understand what those variables represent. It needs to be clear as to what goes with what, and what these different letters and subscripts and so forth represent.